September 19, 1943. Rechlin Testing Facility, Mecklenburg-Vorpommern, Germany. 3 Luftwaffe engineers stood in the cavernous hangar before a Republic P-47C Thunderbolt, its olive-drab paint scorched and streaked with hydraulic fluid from the emergency landing that had brought it into German hands 2 weeks earlier. The aircraft bore the markings of the 78th Fighter Group, shot down during an escort mission over the Low Countries by a pair of Fokker-Wulf 192s, whose pilots had reported something unusual about this particular American fighter before it descended trailing smoke toward occupied territory. What drew the engineers' attention was not the airframe itself, massive though it was, nor the 850 caliber machine guns bristling from its wings. Their focus centered entirely on what lay beneath the engine cowling. The Pratt & Whitney R2000 800 double wasp radial engine, all 18 cylinders of it, represented familiar American engineering, powerful but conventional. What was not conventional, what had already consumed 3 days of careful disassembly and measurement, was the device mounted behind that engine. A General Electric B-series turbo-supercharger that represented a technical approach. German engine designers had explored theoretically but never successfully implemented in operational fighters. The lead engineer, Oberingenieur Klaus Rothmann, a specialist in high-altitude engine performance, who had spent the previous decade working on supercharger development at Daimler-Benz, made notations in his technical journal as his colleagues completed the removal of the turbo-supercharger assembly. The device, weighing approximately 300 pounds, complete with its associated ducting and control systems, embodied an engineering philosophy fundamentally different from German approaches to solving the same aeronautical problem. How to maintain engine power at altitudes where atmospheric pressure dropped to a fraction of sea level values. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German fighters relied almost exclusively on mechanically driven superchargers, devices that compressed incoming air before it entered the engine cylinders, powered directly by the engine's crankshaft through gears and clutches. This approach worked adequately but consumed substantial engine power to drive the supercharger itself, power that could not simultaneously contribute to propelling the aircraft. The American turbo-supercharger, sitting on the workbench, before Rothmann operated on entirely different principles, harnessing exhaust gases, energy that would otherwise be wasted, to spin a turbine that drove the compressor wheel. The implications were staggering. An engine equipped with a properly functioning turbo-supercharger could maintain sea-level manifold pressure at altitudes exceeding 30,000 feet without sacrificing mechanical power to drive the compression system. This meant more power available for propulsion at high altitude, faster speeds, better climb rates, and sustained performance in the thin air where American bomber formations operated, and where German interceptors struggled with engines gasping for insufficient oxygen. The Luftwaffe had known about American turbo-supercharger development for years. Intelligence reports dating back to 1938 mentioned experimental installations. Captured technical literature described theoretical advantages. But theory and battlefield reality occupied different universes. Now, with the physical device disassembled before them, German engineers could examine precisely how American designers had solved the formidable technical challenges that had stymied German attempts at similar systems. The story of how turbo-superchargers came to define American high-altitude fighter supremacy begins not with the war, but with the peacetime work of Sanford Moss, a brilliant engineer working for General Electric, who understood that exhaust gases from internal combustion engines possessed substantial energy in the form of heat and pressure. That energy, he reasoned, could be captured and converted into useful work rather than simply vented into the atmosphere as waste. The concept traced back even further, to Swiss engineer Alfred Büchi, who patented turbocharged diesel engine designs in 1905. But adapting the principle to aircraft piston engines required solving extraordinary technical challenges. Exhaust gases from aviation engines reached temperatures exceeding 1400 degrees Fahrenheit. Materials had to withstand these temperatures while spinning at rotational speeds exceeding 20,000 revolutions per minute. Bearings had to function reliably in environments where thermal expansion, corrosive exhaust gases, and centrifugal forces conspired to destroy conventional designs. Control systems had to manage boost pressure precisely across varying altitudes and power settings without allowing destructive overboosting or inadequate compression. Moss conducted his pioneering work at General Electric's Lynn, Massachusetts facility, beginning in 1918, initially focusing on Liberty engines that powered American aircraft during the First World War. Early results proved promising enough to sustain development funding through the 1920s, despite limited military interest during that era of constrained defense budgets and isolationist foreign policy. The U.S. Army Air Corps maintained small-scale development programs, recognizing that future conflicts might require high-altitude performance capabilities that naturally aspirated engines could not provide. By 1938, General Electric had developed increasingly sophisticated turbo-supercharger designs, designated with letter codes, B Series, C Series, and eventually the refined units that would power American fighters and bombers throughout World War II. The Pratt & Whitney R2800 double wasp engine that powered the P-47 Thunderbolt generated approximately 2,000 horsepower at sea level through conventional mechanical supercharging. The same engine, equipped with a General Electric CH-5 turbo-supercharger, could maintain that power output at altitudes where unassisted engines produced barely half their rated horsepower. Republic Aviation's design team, led by Alexander Kartveli, had conceived the P-47 specifically around exploiting turbo-supercharger capabilities. The aircraft's distinctive deep fuselage, often mocked by pilots as resembling a milk jug or beer barrel, existed primarily to accommodate the complex ducting required to route exhaust gases from the engine mounted in the nose, rearward to the turbo-supercharger located behind the cockpit, then route compressed air forward again to the engine's intake manifold. This configuration required approximately 15 feet of ducting, carefully shaped and insulated to manage gases exceeding 1,000 degrees while maintaining structural integrity and minimizing pressure losses. The result was an aircraft that weighed over 10,000 pounds empty, making it the heaviest single-engine fighter in operational service with any air force during 1943. Critics called it a flying tank, questioned whether such a massive machine could maneuver effectively in combat, and predicted it would prove inferior to more nimble German fighters in dogfighting situations. These critics fundamentally misunderstood the P-47's design philosophy and intended operational role. The Thunderbolt was never designed to be a lightweight turner that excelled in slow-speed maneuvering combat at medium altitudes. It was specifically engineered to climb rapidly to extreme altitudes, escort heavy bombers operating at 25 to 30,000 feet, and fight effectively in that rarefied environment where turbo-supercharging provided decisive performance advantages that lightweight German fighters with mechanically driven single-stage superchargers could not match. German fighter development had followed markedly different paths, shaped by different operational requirements and technical philosophies. The Messerschmitt Bf 109, backbone of Luftwaffe fighter forces since the Spanish Civil War, employed a liquid-cooled inline engine. The Daimler-Benz DB 601 inches early versions, progressing to the more powerful DB 605 inches, the Bf 109G variants that dominated production from 1942 onward. These engines used mechanically driven single-stage superchargers that provided adequate performance to approximately 20,000 feet, but suffered significant power loss at higher altitudes, where compressor efficiency degraded and air density diminished. The Focke-Wulf FW 190, introduced to combat in 1941, used the BMW 801 radial engine, also equipped with a mechanically driven supercharger. This configuration provided excellent performance at low to medium altitudes, making the Fur 190A particularly effective against RAF fighters operating over France and the Low Countries during 1941 and 1942. But like the Bf 109, the Tupolev 190A's performance degraded noticeably above 20,000 feet, precisely the altitude band where American heavy bombers operated. German engineers understood the theoretical advantages of turbo-supercharging. Daimler-Benz and Junkers both conducted development programs exploring turbocharged installations for various engines during the late 1930s. Heinkel's He-177 heavy bomber employed turbocharged Daimler-Benz DB606 and DB610 engines, essentially paired DB601 or DB605 engines driving single propellers. But these installations proved mechanically complex, suffered chronic reliability problems, and experienced catastrophic failures that contributed to the He-177's notorious tendency to catch fire in flight. Fighter applications proved even more challenging. The tight packaging constraints of single-engine fighters left minimal space for the bulky ducting turbo-superchargers required. The additional weight compromised the light, nimble handling characteristics German fighter doctrine emphasized. Most critically, German metallurgy struggled to produce alloys that could reliably withstand the extreme temperatures and stresses turbo-supercharger turbines experienced during sustained high-power operation. The United States possessed significant advantages in specialized high-temperature alloy development, benefiting from unrestricted access to strategic materials like nickel, chromium, and molybdenum required for advanced steel alloys. American research institutions and corporations, including General Electric, Pratt & Whitney, and Wright Aeronautical, invested heavily in metallurgical research throughout the 1930s, developing proprietary alloys specifically for turbine applications. These materials could maintain structural integrity and resist oxidation at temperatures that would quickly destroy conventional steels. Germany faced increasingly severe restrictions on strategic material availability as the war progressed. Nickel supplies from New Caledonia ceased when France fell. Finnish nickel mines provided some supply but insufficient quantities for expanding military production. Chromium from Turkey and the Balkans remained available, but competed with demands from armor plate production and other critical applications. German metallurgists developed substitute alloys using available materials, but these alternatives generally proved inferior in high-temperature performance compared to American nickel-chromium steels. Beyond metallurgical challenges, turbo-supercharger installations required sophisticated control systems to prevent overboosting that could destroy engines through detonation or excessive cylinder pressures. The General Electric systems employed in American fighters used wastegates, controllable valves that regulated how much exhaust gas flowed through the turbine versus bypassing directly to atmosphere. Pilots could manually adjust wastegate position, or in more advanced installations, automatic controllers maintained desired manifold pressure across varying altitudes and throttle settings. German attempts at similar control systems encountered difficulties achieving reliable operation across the full range of combat conditions. Controllers that functioned acceptably during test flights sometimes failed catastrophically during combat maneuvers involving rapid throttle changes and extreme attitudes. The Luftwaffe, facing immediate operational pressures to field effective fighters in large numbers, pragmatically emphasized proven mechanically supercharged designs that could be manufactured reliably using available materials and production facilities, rather than pursuing technically ambitious but problematic turbocharged installations. This decision made sense within the strategic context of 1940 through 1942, when Luftwaffe fighters primarily engaged opponents at low to medium altitudes, where mechanical supercharging provided adequate performance. The Battle of Britain, the Channel battles of 1941 and 42, and even early Eastern Front operations occurred predominantly below 20,000 feet, where German fighters competed effectively against Spitfires, Hurricanes, and Soviet types. The arrival of American heavy bombers operating at altitudes between 25 and 30,000 feet fundamentally altered the equation. The Boeing B-17 Flying Fortress and consolidated B-24 Liberator conducted their bombing runs in an altitude band specifically chosen to complicate German interception efforts. At these heights, German fighters struggled with reduced engine power, degraded climb rates, and diminished maneuverability, while American bombers, themselves equipped with turbocharged engines, operated at optimal efficiency. The P-47 Thunderbolt began arriving in England during late 1942 and early 1943, equipping the 56th, 78th, and 4th Fighter Groups of the 8th Air Force. Initial combat operations revealed teething problems common to new aircraft types entering service. The P-47's Pratt & Whitney R2800 engine occasionally cut out during high-altitude combat maneuvers when pilots pushed the control stick forward abruptly, creating negative G-forces that temporarily interrupted fuel flow. This dangerous characteristic cost several aircraft and pilots before engineers implemented modifications, including improved fuel system components and revised operational procedures. Radio equipment proved unreliable initially, limiting coordination between flights and reducing tactical effectiveness. The aircraft's sheer size and weight made it less nimble in turning combat compared to Bf 109 seconds and FU-EBW 190 seconds, requiring American pilots to adapt tactics that emphasized the Thunderbolt's strengths, speed, altitude performance, and devastating firepower from 850 caliber Browning machine guns, while avoiding sustained turning engagements where lighter German fighters held advantages. Despite these initial challenges, P-47 units achieved growing success through spring and summer of 1943 as pilots learned to exploit their aircraft's capabilities. The Thunderbolt could climb rapidly to altitude, cruise efficiently at 30,000 feet where German fighters labored, dive at speeds exceeding 500 miles per hour without structural failure or control problems, and fight effectively throughout the high-altitude envelope where bomber escort combat occurred. German pilots encountering P-47 seconds during mid-1943 reported frustration at their inability to catch the American fighters when Thunderbolt pilots chose to disengage. The P-47's excellent dive and performance, enabled partly by its substantial weight and partly by its robust structural design, allowed it to accelerate away from pursuing German fighters whose lighter structures and different design philosophies imposed more conservative dive speed limits. Messerschmitt Bf 109Gs experienced severe control, stiffening at high speeds, making recovery from steep dives physically demanding and potentially dangerous. Focke-Wulf 190 as handled high-speed dives better than Bf 109 seconds, but still could not safely match the Thunderbolt's terminal velocity. Luftwaffe intelligence officers collected pilot reports describing these encounters, but initially struggled to understand the source of the P-47's high-altitude advantage. The aircraft was obviously large and heavy. Its radial engine appeared similar to the BMW 801, powering W190 seconds. Why then did it perform so dramatically better at altitude, where air density should equally disadvantage all piston engines, regardless of configuration? The answer lay in the turbo-supercharger system that German engineers were now examining with minute attention at Rechlin. Rothmann directed his assistants to measure every dimension of the turbine housing, the compressor section, the wastegate valve, and the intercooler that cooled compressed air before it entered the engine's intake manifold. They photographed components from multiple angles, creating detailed documentation that would be analyzed by specialists at research facilities across Germany. The turbine wheel, machined from specialized high-temperature alloy, measured approximately 9 inches in diameter, with precisely contoured blades designed to extract maximum energy from exhaust gases. The compressor wheel, mounted on the same shaft and spinning at identical rotational speed, compressed ambient air drawn from intakes located on either side of the P-47's fuselage behind the engine cowling. This compressed air, heated by the compression process itself, passed through an intercooler that used ram air to reduce temperature before the charge entered the engine's cylinders. Intercooling represented another sophisticated refinement that improved system efficiency. Cooler air was denser, allowing more oxygen molecules per unit volume into the cylinders, where they supported combustion. The P-47's intercooler added complexity, weight, and additional ducting to the installation, but provided measurable performance improvements that justified these costs. German engineers noted the intercooler's design carefully, recognizing it as evidence of thorough American attention to thermodynamic optimization. The wastegate system revealed particularly clever engineering. A butterfly valve controlled by a pneumatic actuator regulated exhaust gas flow through the turbine. When fully closed, all exhaust gases passed through the turbine, spinning it at maximum speed and generating maximum boost pressure. As the wastegate opened progressively, increasing amounts of exhaust bypassed the turbine, reducing turbine speed and boost pressure proportionally. This variable control allowed pilots to maintain desired manifold pressure across varying altitudes and power settings. An automatic regulator, responsive to manifold pressure feedback, could maintain preset boost levels without constant pilot intervention, reducing workload during complex combat maneuvering. German pilots flying Bf 109 seconds and FW 190 seconds manually controlled their mechanically driven superchargers through gear-shifting mechanisms or clutch systems that engaged different impeller speeds. These systems required careful coordination with throttle adjustments and altitude changes, adding to pilot workload precisely when combat situations demanded maximum attention to tactics and situational awareness. Rothmann's examination revealed the extraordinary precision required throughout the turbo-supercharger system. Turbine and compressor wheels spun on bearings that had to maintain alignment to within thousandths of an inch while operating at temperatures exceeding 600 degrees Celsius and rotational speeds where blade tips approached supersonic velocity. Any imbalance, any degradation of bearing surfaces, any misalignment of components would cause catastrophic failure, potentially destroying not just the turbo-supercharger, but the entire engine through fragmentation or fire. American engineers had solved these challenges through superior metallurgy, precise manufacturing tolerances maintained across thousands of production units, and robust quality control that ensured consistent reliability. German industrial practices, particularly by 1943, as Allied strategic bombing intensified, and production dispersed to smaller facilities using increasingly unskilled labor, including forced workers, struggled to maintain the consistency required for such demanding applications. The captured P-47s maintenance records, recovered with the aircraft, revealed another sobering reality. The turbo-supercharger installation required specialized maintenance procedures and periodic inspections, but the system generally proved reliable in operational service. American ground crews, equipped with proper tools, genuine spare parts, and comprehensive technical manuals, could service and repair turbo-supercharger systems efficiently. The 8th Air Force in England operated an extensive logistics network that supplied fighter groups with necessary parts, technical support, and specialized expertise. Germany's increasingly strained logistics system could not replicate this support infrastructure even for existing German aircraft types, much less for hypothetical turbocharged fighters that would require entirely new supply chains, specialized tools, and technician training programs. Even if German engineers could design functionally equivalent turbo-supercharger systems using available materials, manufacturing them in quantity while maintaining necessary quality standards represented an almost insurmountable challenge given resource constraints and production disruptions. Rothmann composed a preliminary technical report summarizing initial findings from the P-47 examination. The report, classified secret and distributed to relevant Luftwaffe commands and aircraft manufacturers, acknowledged American achievement in developing operationally reliable turbocharged fighter installations. It noted specific technical features that enabled the system's success, including superior high-temperature alloys, precision manufacturing, effective intercooling, and sophisticated automatic controls. The report concluded somewhat pessimistically that replicating American turbo-supercharger technology would require Germany to solve multiple interconnected challenges simultaneously, developing equivalent high-temperature alloys despite strategic material shortages, achieving precision manufacturing despite industrial disruption and labor quality degradation, creating reliable automatic controls despite limited experience with such systems, and integrating these components into fighter airframes already optimized around different propulsion concepts. Even if these technical obstacles could be overcome, the report estimated that fielding operationally viable turbocharged German fighters in meaningful numbers would require at minimum 18 to 24 months, assuming adequate priority and resource allocation. By late 1943, with Allied strategic bombing intensifying, the Eastern Front consuming enormous resources, and overall German strategic position deteriorating, committing substantial development effort to turbocharged fighter programs appeared questionable compared to alternative approaches, offering faster results. German fighter development consequently emphasized different technical solutions to the high-altitude performance challenge. Daimler-Benz developed improved mechanical supercharger systems, including two-stage installations that provided better altitude performance than single-stage designs, though still inferior to turbo-supercharging. The DB605 AS engine used in some Bf109G variants employed a larger supercharger impeller and different gear ratios optimized for high-altitude operation, improving performance above 25,000 feet at the cost of reduced low-altitude power. Focke-Wulf developed the WWII series, substituting the BMW 801 radial engine with the liquid-cooled Junkers Jumo 213 inline engine equipped with a sophisticated two-stage mechanical supercharger. The FOF 190D, particularly the D9 variant that entered service in late 1944, offered significantly improved high-altitude performance compared to earlier FOF 190A models. But development delays, production challenges, and the rapidly deteriorating war situation prevented the WFW 190D from appearing in sufficient numbers to materially affect strategic outcomes. The TAR 152, an even more specialized high-altitude development of the FOR 190 designed by Kurt Tank, employed a Junkers Jumo 213E engine with 3-speed mechanical supercharger and MW50 methanol water injection for additional power boost. The TAR 152H could operate effectively above 40,000 feet, exceeding even the P-47's service ceiling. But fewer than 200 TAR 152 seconds of all variants reached operational units before the war ended, far too few to challenge Allied air supremacy or protect German cities from high-altitude bombardment. These developments, while technically impressive and demonstrating continued German engineering competence under extraordinarily difficult circumstances, arrived too late and in insufficient quantities to reverse the strategic balance that had shifted decisively against Germany by mid-1944. The Luftwaffe's fighter force faced overwhelming numerical disadvantage, chronic fuel shortages that limited both training and operations, unsustainable pilot attrition, and infrastructure degradation from relentless Allied bombing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination of the captured P-47 at Rechlin continued for several weeks, as specialists from various research establishments visited to study specific subsystems. Engine experts analyzed the R2800's cylinder head design, valve arrangement, and crankshaft construction. Armament specialists examined the installation of 8 Browning M2 machine guns with their ammunition feed systems and gun heaters that prevented weapons from freezing at extreme altitude. Radio equipment underwent detailed evaluation, revealing the sophistication of American communication systems compared to often unreliable German radios. Each technical area revealed American advantages in design maturity, manufacturing quality, or both. The P-47's hydraulic system demonstrated reliability and thoughtful component placement. Electrical systems used standardized connectors and logical wire routing that simplified maintenance. Flight controls employed pushrod linkages rather than cables, providing more positive control response with less maintenance requirement. Even seemingly minor details like access panels positioned for convenient servicing revealed attention to practical operational considerations. German test pilots eventually flew the repaired P-47, experiencing firsthand its performance characteristics and handling qualities. Hauptmann Heinrich Baer, a highly experienced fighter pilot with over 200 victories primarily on the Eastern Front, flew evaluation flights at Rechlin during late 1943. Baer reported being impressed by the Thunderbolt's high-altitude performance and its docile, stable handling characteristics that made it relatively easy to fly despite its size and weight. He noted the excellent visibility from the cockpit, comfortable seating position, and logical instrument layout that reduced pilot workload. The aircraft accelerated impressively in dives, reaching speeds where German fighters experienced severe control problems, while the P-47 remained stable and controllable. Most significantly, Baer confirmed that at altitudes above 25,000 feet, the Thunderbolt possessed clear performance advantages over German fighters in speed, climb rate, and sustained combat capability. The tactical implications deeply concerned Luftwaffe commanders, who understood that American bombers operated precisely in the altitude band, where German fighters now faced systematic disadvantage. Fighter pilots attempting to intercept bomber formations at 28,000 feet found themselves engaging not just the bomber's defensive firepower, but also escort fighters that possessed superior speed, climb performance, and endurance at those altitudes. The P-47's combat radius, while initially limited compared to the later P-51 Mustang, still exceeded that of Bf 109 seconds and FW 190 seconds by comfortable margins, allowing American escorts to accompany bombers deeper into German territory than previous Allied fighters could manage. German pilots developed tactics attempting to mitigate these disadvantages. One approach involved climbing well above expected bomber altitudes, sometimes to 35,000 feet or higher, then diving through escort screens to attack bomber formations with speed accumulated during the descent. This tactic occasionally succeeded, but required perfect timing and coordination while exposing attacking fighters to devastating fire from bomber defensive guns during the brief attack window, before they had to break away and escape. P-47 pilots learned to position themselves above German fighter formations whenever possible, denying Germans the altitude advantage while threatening diving attacks that German pilots could not easily escape. The Thunderbolt's robust construction and pilot protection, including thick armor plate behind the seat and bulletproof windscreen glass, allowed it to absorb battle damage that would have destroyed lighter fighters. Pilots returned to base with holes from 20mm cannon shells through wings, fuselage, and even engine cylinders, testimony to the aircraft's survivability under combat conditions. The psychological impact on Luftwaffe pilots confronting these increasingly capable American fighters extended beyond simple tactical frustration. Many German pilots had entered the war confident in their superior training, the quality of their aircraft, and the effectiveness of their tactical doctrines. By late 1943, that confidence had eroded significantly through repeated encounters with opponents who possessed not just numerical superiority, but also technical advantages in critical performance areas. German propaganda continued proclaiming the superiority of German technology and the inevitable defeat of Allied forces, despite growing evidence to the contrary. Pilots returning from combat missions over Germany reported honestly about American fighter capabilities, often contradicting official narratives about German technical supremacy. This created cognitive dissonance between official messaging and observable battlefield reality, contributing to declining morale among pilots, who increasingly felt they were being asked to perform impossible missions with inadequate resources. The captured P-47 examination at Rechlin provided concrete, undeniable evidence that American aviation engineering had achieved parity with or superiority over German capabilities in multiple critical areas. The turbo-supercharger system represented perhaps the most visible example, but broader patterns emerged from systematic technical analysis. American manufacturing demonstrated consistent quality across thousands of aircraft. American metallurgy produced specialized alloys unavailable to German industry. American logistics sustained operations across vast distances with remarkable efficiency. These realizations forced acknowledgement among German technical experts that Allied industrial and technological capabilities exceeded pre-war assumptions significantly. The comfortable narrative that portrayed Americans as capable of mass production but incapable of sophisticated engineering collapsed when confronted with hardware evidence. The P-47 was not a crude, simple machine produced in quantity at the expense of quality. It was a refined, capable weapon system that successfully integrated advanced technologies into an effective operational platform manufactured at scale with consistent quality. Production statistics told a sobering story about relative industrial capacity. Republic Aviation produced over 15,000 P-47 Thunderbolts between 1942 and 1945, with peak monthly production exceeding 1,000 aircraft during 1944. This output for a single fighter type exceeded total German production of all fighter types during comparable periods. Moreover, American factories simultaneously produced thousands of P-51 Mustangs, P-38 Lightnings, naval fighters, and bombers while maintaining quality standards that German industry, increasingly disrupted by strategic bombing and resource shortages, struggled to match. The turbo-supercharger systems installed in these thousands of P-47s functioned reliably in operational service, requiring maintenance, but not experiencing catastrophic failure rates that would have grounded the fleet. This reliability across large production quantities demonstrated mature manufacturing processes, effective quality control, and robust design that tolerated normal production variations without compromising functionality. German attempts to rapidly expand production of existing designs often resulted in declining quality as less skilled workers using substitute materials assembled aircraft in dispersed facilities with inadequate tooling and supervision. Reichsmarschall Hermann Göring, commander of the Luftwaffe, received regular intelligence briefings about American aircraft capabilities, including detailed technical reports from Rechlin examinations. Göring's responses to this information varied from denial to rage, sometimes blaming intelligence officers for defeatism when they reported uncomfortable truths about Allied technical advantages. His insistence on promoting unrealistic wonder weapons and jet fighter programs diverted resources from incremental improvements to existing types that might have provided more practical near-term benefits. The Messerschmitt Me-262 jet fighter represented Germany's most ambitious attempt to leapfrog Allied piston-engine fighter performance through revolutionary turbojet propulsion. The Me-262 possessed substantial speed advantages over any Allied piston fighter, reaching 540 miles per hour in level flight, well beyond what P-47 seconds or P-51 seconds could achieve. However, the Me-262 program suffered from multiple critical problems that prevented it from achieving strategic impact despite its impressive technical specifications. Junkers Jumo 004 turbojet engines that powered the Me-262 proved chronically unreliable, suffering from turbine blade failures caused by inadequate high-temperature alloys forced on designers by strategic material shortages. Engine operational life rarely exceeded 25 hours before requiring replacement or major overhaul, compared to hundreds of hours for American piston engines. The Me-262 required long concrete runways for takeoff and landing, making it vulnerable to Allied fighter patrols that learned to attack jets during these critical phases when their speed advantage was neutralized. Most critically, Me-262 production and deployment occurred far too late and in far too limited numbers to materially affect strategic outcomes. Approximately 1,400 Me-262 seconds were manufactured, but only a fraction reached operational units, and pilot training, fuel availability, and spare parts shortages severely limited sortie rates. Even when flown by skilled pilots against American bomber formations, individual Me-262 seconds could not compensate for overwhelming Allied numerical superiority and the systematic destruction of German aviation infrastructure. The examination of captured American aircraft continued throughout 1944 and into 1945, as German forces recovered additional examples from crash sites across occupied Europe and within Germany itself. Each technical evaluation added to the accumulated evidence that Allied aviation technology matched or exceeded German capabilities, while Allied industrial capacity operated at scales Germany could not approach given strategic constraints and resource limitations. A particularly revealing example involved the examination of P-47D models captured during late 1944. These later production Thunderbolts incorporated numerous refinements based on operational experience, including improved turbo-supercharger regulators, upgraded radio equipment, and strengthened wing structures for carrying external ordnance. German engineers noted that American designers continued improving their aircraft through systematic analysis of combat reports and technical feedback from operational units, demonstrating an effective development process that rapidly incorporated lessons learned. German fighter development, by contrast, increasingly struggled with resource constraints, production disruptions, and bureaucratic interference that delayed or prevented implementation of needed improvements. The Bf-109 continued in production through the war's end, despite being fundamentally a late 1930s design, stretched beyond its optimal development potential through successive modifications. The aircraft remained competitive through pilot skill and tactical employment rather than technical superiority, fighting at systematic disadvantage against newer Allied types. The human cost of these technical disparities manifested in Luftwaffe pilot casualties that reached unsustainable levels during 1944. Experienced pilots who understood through combat how to maximize their aircraft's remaining advantages while minimizing exposure to enemy strengths were killed or seriously wounded faster than replacement pilots could be trained. New pilots arrived at operational units with minimal flight time, often less than 100 hours total, compared to American pilots who typically received 300 to 400 hours of comprehensive training before entering combat. These inadequately trained German pilots flying inferior or at best equal aircraft against numerically superior and technically advantaged opponents survived an average of only a handful of combat missions before being shot down. The Luftwaffe was consuming its most irreplaceable resource: skilled, experienced pilots who possessed the judgment and tactical knowledge necessary for survival and effectiveness in combat, at rates that guaranteed eventual collapse regardless of aircraft production numbers or technical improvements. Fuel shortages compounded every other problem facing the Luftwaffe during the war's final year. Allied strategic bombing systematically destroyed German synthetic fuel production facilities, reducing aviation gasoline availability to fractions of operational requirements. Fighter units received fuel allocations barely sufficient for defensive sorties, forcing cancellation of training flights that might have improved pilot preparation. Aircraft sat grounded not because they were damaged or lacking pilots, but simply because no fuel existed to operate them. The P-47 Thunderbolt, powered by its turbocharged R2800 engine, and supported by Allied logistics networks that delivered thousands of gallons of high-octane aviation fuel to English airfields daily, faced no comparable constraints. American fighter groups flew multiple missions daily, limited only by pilot fatigue, aircraft maintenance requirements, and weather conditions. This operational tempo sustained continuous pressure on German defenses, degrading effectiveness through cumulative attrition that Germany could not sustain or counter. The technical intelligence gathered from examining captured P-47 seconds contributed to German understanding of Allied capabilities, but could not bridge the fundamental gaps in industrial capacity, resource availability, and strategic position that characterized the air war by 1944. German engineers produced detailed technical reports documenting P-47 systems and performance. These reports informed German fighter designers about American approaches and validated observations from combat pilots. But knowledge alone could not overcome material and industrial disadvantages of the magnitude Germany faced. Some German engineers, recognizing the sophistication of American turbo-supercharger technology and the unlikelihood of replicating it under wartime constraints, advocated alternative approaches to improving high-altitude performance. These included two-stage mechanical supercharging as implemented in various late-war engine developments, nitrous oxide or methanol water injection systems that temporarily boosted power output, and pressure cabin installations that allowed pilots to operate effectively at extreme altitudes without oxygen masks that restricted vision and communication. Each approach offered partial solutions but came with significant trade-offs. Two-stage mechanical superchargers improved high-altitude performance but added weight, complexity, and consumed engine power to drive the compression stages. Nitrous oxide and methanol water injection provided temporary power boosts but required additional tanks, plumbing, and control systems while limiting boost duration to a few minutes per sortie. Pressure cabins improved pilot effectiveness but added substantial weight and complexity while creating potential catastrophic failure modes if struck by enemy fire. None of these alternatives matched the comprehensive advantages turbo-supercharging provided. Sustained high-power output at altitude without significant weight penalty beyond the turbocharger installation itself, utilizing waste exhaust energy rather than consuming mechanical power, and relatively simple operation requiring minimal pilot workload. American engineers had invested 2 decades refining turbo-supercharger technology, solving countless detailed problems through patient development work backed by adequate funding and access to necessary materials. German attempts to compress similar development into months rather than years while operating under wartime urgency and resource constraints predictably encountered difficulties that delayed or prevented successful implementation. The few German turbocharged aircraft that reached operational service, primarily heavy bombers and reconnaissance types, suffered reliability problems that reinforced skepticism about the technology's suitability for fighter applications, where weight, complexity, and maintenance requirements directly impacted combat effectiveness. By early 1945, as Allied armies advanced into Germany from both east and west, the Luftwaffe had effectively ceased functioning as a coherent defensive force capable of meaningful resistance. Individual units still flew when fuel permitted, sometimes achieving local tactical successes against isolated Allied formations. But systematic air defense of German territory and industry had collapsed under overwhelming Allied numerical superiority, unsustainable German losses, and infrastructure destruction that prevented effective coordination of remaining forces. The captured P-47 examined so carefully at Rechlin during late 1943 represented just one aircraft among thousands that established and maintained Allied air supremacy over Europe during 1944 and 1945. The technical intelligence gathered from its examination informed German understanding of American capabilities, without providing practical means to counter those capabilities given strategic constraints. German engineers recognized and could appreciate American engineering achievement even while serving a regime whose policies had created the strategic circumstances ensuring Germany's defeat. The turbo-supercharger system that so impressed Rothmann and his colleagues embodied decades of American engineering development, substantial industrial investment, unrestricted access to strategic materials, and systematic refinement through testing and operational experience. Germany could not replicate these advantages during wartime, particularly after 1943, when Allied strategic bombing disrupted production, resource shortages, constrained material choices, and overall strategic position deteriorated beyond recovery. The story of Luftwaffe engineers examining captured P-47 superchargers illustrates how technical intelligence gathering, no matter how thorough or professionally executed, cannot overcome fundamental disparities in industrial capacity, resource availability, and strategic position. German engineers produced accurate, detailed assessments of American technology. They understood precisely how turbo-superchargers functioned and why they provided decisive advantages. But understanding did not translate into ability to field equivalent systems under the constraints Germany faced. The admission implicit in German technical reports that American turbo-supercharger technology could not be quickly replicated represented professional acknowledgement of Allied engineering achievement and realistic assessment of German limitations. This acknowledgement, forced by examination of physical hardware rather than shaped by propaganda or wishful thinking, contributed to growing recognition among German technical experts that Allied industrial and technological capabilities exceeded pre-war assumptions fundamentally. The P-47 Thunderbolt continued serving effectively throughout the war's remainder and into post-war service with multiple air forces. Over 15,000 were built, establishing the type as one of history's most produced fighter aircraft. The turbo-supercharger technology that provided its high-altitude advantage became standard in American combat aircraft development, influencing post-war designs and contributing to American aviation industry leadership during the early jet age, when similar principles applied to turbojet development. German aviation engineering, despite producing innovative designs and demonstrating continued technical competence under extraordinarily difficult circumstances, could not overcome the cumulative disadvantages imposed by strategic bombing, resource shortages, industrial disruption, and fundamental material constraints. The examination of captured American aircraft provided knowledge without providing means to apply that knowledge effectively given wartime realities. The engineers who studied the P-47's turbo-supercharger at Rechlin during September 1943 understood they were examining technology Germany could not match under existing circumstances. Their detailed technical reports documented American achievement while implicitly acknowledging German inability to counter it adequately. This knowledge, professionally gathered and honestly reported, contributed to realistic assessment of German strategic position among those willing to accept uncomfortable truths about relative capabilities. The turbo-supercharger removed from that captured P-47, weighed and measured and photographed from every angle, represented American engineering philosophy that prioritized practical effectiveness over theoretical elegance, reliable operation over maximum performance, and systematic development over rushed improvisation. These priorities, combined with superior industrial capacity and unrestricted material access, produced operational advantages that skilled German pilots flying inferior equipment at numerical disadvantage could not overcome through courage or tactical competence. Victory in industrial warfare belonged to nations that could outproduce, outdevelop, and ultimately outlast their opponents through superior resource access and more efficient conversion of those resources into effective military capability. The P-47 Thunderbolt and its turbocharged R-2800 engine exemplified this reality, turning theoretical engineering advantages into decisive battlefield superiority through reliable implementation at massive scale. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.